Okay, welcome back, everybody. We are going to continue our discussion on multivariate homotopy continuation today. Specifically, we'll derive the multivariate Davydenko differential equation. We will talk about what an Euler step looks like. We'll talk about what a Newton step looks like. And to begin, I just want to remind us of an example that we ended on last class, which was this. So let's call this plane curve. So this is a variety in the plane. It's a curve because if you're a little bug here, you can only go forward or backwards, so it's one-dimensional. One-dimensional things are called curves. And it is the zero set of this equation. Think about this whole system as F. We have that dF. We're also calling the Jacobian of F. Looks like, what was this? Negative 3x squared minus 2x, 1, 2, 1. And geometrically, what the Jacobian tells us about this curve is its kernel is the Zariski tangent space of the variety at one of these points. So for example, if I choose the point, x is going to be -1, 0, and we plug this in, okay, we're going to get something here that's not 0. We're going to get 0 here. And so the Jacobian of F evaluated at the point being -1, 0 as a kernel, which is the span of 0, 1. It gives us exactly what we think is the which, because of linear algebra, the row space is orthogonal to this. The row space is giving you some normal space. And that works at the so-called smooth points. So a point on a dimensional variety is smooth, say a point P, if the dimension of the kernel of the Jacobian evaluated P say this is this tangent space, which we write I suppose we can just assume this for the whole class, but we're assuming that x is cut out by the equations now. Otherwise, if the dimension of the tangent space is greater than k, then T is a singular point. The right. So 0, 0 here is a singular point. Well, why? Okay, so here, if I plug a random x and y on this variety in, I'm going to get that at least one of these is non-zero. And so the generic rank of the Jacobian here is 1. So rank nullity tells me that the generic dimension of the kernel is 1. So 1 plus 1 has to equal the number of columns. Okay, so that's the dimension of the variety. And when the dimension of this kernel is larger, in other words, the rank of this matrix is smaller, then we have a single. And 0, 0, if we plug in here, indeed gives us the matrix 0, 0, which has rank 0. So the kernel has dimension 2. And so that means that's a singular. Okay, so the kernel is not really giving what we intuitively would think of as like tangent directions at the point. It's really saying every direction is a tangent direction. So this is the Zariski tangent space. But there's another way to describe this variety. So we mentioned that varieties can kind of be described in two ways. That's how they'll come at you. The first way is via implicit equations. So via the actual definition of a variety. It's the zero set of polynomials. But the other way is as the image of some map, or specifically as the smallest variety containing the image of a map. So not every variety can be described this way, but some can, and in particular, this one can. So P is going to go from here to here, and P will go to T squared minus 1, T cubed minus. So T you think of as some time parameter, and like usual, when you parameterize something, you think about drawing it, like literally drawing it at time 1, you're at 0.1, and time 2, you're at 0.2, and you're drawing this thing. And it's drawn like this. Yes, go ahead.
This might be unrelated, but if I choose, say, any other parameterization, can I say choose, say, some arc length parameterization, for example? Can I avoid that point where the issue is happening? Or is it not the issue of parameterization, but it is the issue of the curve itself? Which one? Say you can take it, say another parameterization of this, arc length parameterization, and avoid the curving. Yeah, somehow. Can we do that? Or
So the question is, under some other parameterization,
can
can I avoid a certain phenomenon?
Can I avoid that particular point where the Jacobian is problematic?
So I have two comments about this. So the first comment is that there's no need to avoid this point if we've parameterized it. We'll see that here, is that we're actually not going to witness the issue about this Jacobian in this context in the same way that we did before. Because the fact that we have a time parameter and we're drawing actually does give us a well-defined vector when we go through that point at two different time values. Okay, so there are two different t values, which gives us 0, 0 here, t equals 1, t equals negative. And at each of those, there is an actual vector. So the issue why these are not agreeing is because this parameterization is non-injective. So the other question one might say is like, okay, well, can I parameterize this in a way where like maybe I don't parameterize the whole variety, but I just miss this point, but then the closure takes care of that. And that's a different story, and I have to think about that. I would not usually do that.
But to avoid the singular point, this doesn't use the parameterization, right? The definition doesn't use that.
No, what I mean is, in general, say, can we always choose a parameterization that can avoid the singular point?
Okay.
I think the answer is no, but I would have to think hard, especially on record. Okay. Great. So now, if we take the Jacobian of this method. So now, when t is 1, we're at the point 0, 0. And if we valued the Jacobian here, so now the column space of P describes the tangent in a very subtly different way. And so I just wanted to illustrate this difference. For most points, this is exactly the same. But when you have a parameterization and it's not injective, so you have two different point time values where you're going through a point, this can differ in exactly this way. But generally, the column space would then be describing the tangent direction of the parameterization. And indeed at t equals 1, this is the vector 2, 2. And at t equals -1, the second value is the same, first value is negative. So there. Yeah, so that must mean that -1, boom, -1, 1. Okay. Okay, so these are useful gadgets to have. But it's also, as I alluded to earlier, this Jacobian is the differential information we'll need to extend homotopy continuations of multivariate set. All right, so backing up to homotopy continuation, we want to find all the isolated solutions to some square polynomial system in n variables. So n equations, n variables. And what we do is we cook up the Brysiewicz system. And then we build a homotopy. The Brysiewicz system, remember, it's x1 to the degree of the first polynomial f minus 1 all the way up to xn to the degree of the nth polynomial of the target system minus 1. And we'll do the gamma trick right away. Because, well, it's still a homotopy from T to F, even with the gamma, so why not put it, even if we aren't convinced that we need it or anything. Right. We have D equal to the product of the degrees of the FIs. Many solutions here. And this number is called the Brysiewicz bound. Brysiewicz theorem says this is the largest number of isolated zeros that a polynomial system with these degrees could have. Of course, you could have more solutions, but then you'd have infinitely many solutions. Just as before, we'd like to apply implicit function theorem. And if you look it up and you work it out, the condition to be able to do that is that the Jacobian of the corresponding square system is non-singular at this point. Okay. Equivalently, we don't have one of these double roots. And indeed, that is not the case for the Brysiewicz start system. So we can imply implicit function theorem. The rest of the argument is exactly the same. And so we get these paths, just as before. Now these paths we're not sure how badly behaved f is, so we have to do an open interval there. And it goes into C to the n, because that's where the solution space lives. Okay. And so maybe actually I'll kill this notation. I'll put an I up here, because this is still a vector of functions, right? So I don't want this x sub I to be confused with one of these x sub i's. Right, so that was a non-issue in the univariate case, becomes an issue now. So now we are going to reproduce that Vinca. But in order to do that, I'd like to remind you of the multivariate chain. So A, B, and C are all some C to the n for now. And bar P and P are gonna be polynomial maps. Okay, so the question about the chain rule is how do I describe the differential information about the composition of two maps? Okay, so in calculus, we compose two univariate functions going from R to R, and the chain rule tells us what the derivative of that composition is in terms of the derivatives of each. Okay, so we want that for a multivariate setting. So maybe just a show of hands. Have you seen the chain rule in a multivariate setting before? About vector calculus class, perhaps? Yeah, it's one of these things you forget, I think. So let's just look at it again. The thing to remember is that the Jacobian of each of these maps is the best linear approximation of this map, right? And so the only candidate for giving the best linear approximation of the composition would be the composition of those linear transformations. That's the chain. Okay, now you got to write it down in notation, and now it pops what you knew in calculus, but souped up to the multivariate set. So what do? We apply phi first. And so if we want this Jacobian evaluated at some, let's say, A. Well, the first thing we do is we take the Jacobian of phi evaluated at A. Then we multiply it because matrix multiplication is composition of linear transformations with the Jacobian of phi. Evaluated where? No, phi of A. Okay, so d phi composes p is okay, so like if B and B were f and g and they were univariate polynomials, then indeed you get f prime of g of x times g prime of x. So that's what we do. I always like this picture too. Jacobian playing with the maps. Okay, so that's a background on chain rule. Now let's just use it. Okay. So we have these functions, so that xi of t. So this solves the homework. And so now we just want to apply the chain rule to the left-hand side and claim that that's 0. Okay. So I'll give you all a minute to try to work that out by hand. It's kind of fun. If you're online, feel free to pause it, and I'll pause the recording right now to come back. Okay. All right, welcome back. Let's work this out together. Just a notational chase here. So the name of the game is to just identify the Jacobians of each of these maps, and then we can just multiply them together after that. Okay, so here, this is xi cross the identity map on T. It takes in a T value, and it's essentially giving you the graph of x to the I. Okay, it gives you the value of x to the I, and then the T value that comes along. That's the graph of x to the I. And I'm gobbling up one-dimensional things, spitting out n plus one-dimensional things, so let's call this b, I mean, let's just call this x star. We'll just fuck this. All right, so dp here is gonna be okay, so dxi1, because this is the first coordinate, dt all the way to dxi n dt. Then the last thing here, so this t goes to the xi of t comma t. So this last coordinate is t, and its derivative with respect to t is 1. Okay, this is gradient vector dot. Good. We got n plus 1 here, we got 1 here. So at least we're starting and landing in the right places. That passes our first sanity check. Great. Okay, so now for h, well, it's not much you can simplify. There was a bit of notation that was suggested in the last class that's going to help here. And that's that we're just going to write dh here as so this is an n by n, and this is an n by 1. Okay. So this is n by n plus 1, so it gobbles up n plus 1 things, spits out n things. That's good. We didn't accidentally write that down in the transpose. And now the Jacobian of the left-hand side, which is a 1 by n thing, the composition of these two maps, it's just going to be the product of these two. Yeah. Okay. And so we get the equation that dxh dt. That's 1. Oh, that's nice. We kind of split things up in a way where this multiplication can happen nicely. Is 0. But of course, it's not just equal to 0. It's equal to dxh. So like del x plus. Okay, and this is. This works out very nicely. What's the thing we're after again? We're after the differential information of this path. So we really want to solve for this, because this will tell us the vector that this path is going in at any point. Right? And this is well, we've got a negative ETH. Okay. And then we have, this is an n by n matrix, so we're going to have to multiply by its inverse. Take the negative out there, dx h inverse. Okay. And this is Debbie. And indeed, we want to make sure that dxh is invertible. But look, it is as long as yeah, as long as we're generically on this. So it's non-singular here, so it's non-singular locally. Okay. Great. So now, from the Davenport differential equation, we can apply Euler's method, right? So in other words, if you're some vector floating around through space, you don't know what path you're on, but you know what direction you're going, and you want to guess where you're going to be in a little h time step, well, it's that vector times h. That's what an Euler step is. So the Euler step applied to some, say an x, yeah, x star, t star. Just your first order guess. X star. I guess you have some h parameter for a time step. Okay. Euler. Okay, and finally, Newton. If I have some polynomial system F, I want to apply Newton, an x star, x star minus exactly what Newton looked like before. Okay, so before x got updated to be x minus f of x divided by f prime of x. This is the divided by, the inverse. And this is the f prime of x. And we're not going to redirect. Just like we didn't do it in the univariate. Any These are 3 ingredients for homotopy continuation. Well, okay, sorry, that's not true. There's more. So you also need a start system, right? Kind of like implicitly assuming that, but we'll actually switch the start system later in the course. And you need start solutions. And maybe you need some endgame handlers and stuff like this. So what's the story? So now homotopy continuation, polynomial homotopy continuation in n variables. The big picture. Our solution spaces are c to the n's. One thing that's nice is now these points, they're floating in a much higher dimensional space. You might be inclined to think heuristically that these points won't get so close to each other. They have more room to move around each other. That's heuristically true. We might still have points coming together in this. And now we are much more seriously concerned about points flying off to infinity. Now, this never happened with the univariate case. Why didn't this happen in the univariate case?
There was no proof about it.
fundamental theorem of algebra says our target system has n solutions, counting with multiplicity. And the multiplicity agrees with the number of paths leading to it. And so you can't lose a path to infinity, because then you wouldn't have n or degree of f many solutions hit counting multiplicity. That's not the case here. Bezier doesn't say that every polynomial system with this degree sequence has that many roots. It says a random one does. Okay, and non-random ones, so if your adversary picks one, it won't have any more than this many isolated roots. Okay, and that won't have any more is really nice. That's what's going to tell us that we'll hit everything. Okay. But a lot might fly off. Okay, so how bad can it be? Though that's not too hard to come up with. Even in two variables, it can be arbitrarily bad. So here's an example. Can I come up with an example? Yeah. So let's do y equals f of x, where this has degree d. And let's intersect it with a vertical line. Some random a. That only has one solution. Okay. Because functions pass the vertical lines. However, our start system will have two solutions. Okay, so it can be arbitrarily bad. And there's an art to picking new start systems here, so that you don't have all these wasted paths. But that's for next section. This was the picture. Oh, there's one really awful thing that can happen. Is that one of these paths may not be an isolated solution. Okay. Everybody's squinting, that's okay. Imagine somebody handed you a square system that didn't only have isolated solutions. Let's say it cut out like the parabola and then like a dot in the middle. Okay, I think we've last class we saw a formulation of that system. The natural question is, well, what's going on then if I try to do this blindly? If I didn't know there was some infinite many solutions, what's going to happen? Well, you're definitely going to get the isolated solution. Okay, so that's a theorem. But other start systems, they might get lost not by going to infinity, but going onto the parabola at some random point. Okay. So after you get these endpoints, using the computational methods, there is this like nagging question of, is it an isolated solution? Right? So the rank of the Jacobian of f evaluated at x star equals n implies that this is isolated, but the converse is not true. So in both of these situations, the Jacobian drops rank. So the need is to differentiate between these two situations. You can definitely tell when you have isolated solutions. It's the multiplicity that's going to be a problem. When you have multiplicity versus when you have landing on a positive dimensional component. Okay. Your first homework for the second homework assignment is to find an example of a homotopy where this happens. I already gave you one. Okay. Find an example where you get something going off to infinity. We've given one. Find an example with a path crossing. And I think there was, yeah, and then find an example with multiple roots coming together, I think. So I want an example, you to construct an example of each of these bad endgame phenomena. Great, and we got Euler, we got Newton. And so this should work, right? And coding up a crude version of this is your only coding assignment for this, and you can work on it together via the Discord. We'll do like a lot of it today, yeah, in the coding section. So just make sure you understand it and can reproduce things, okay? We'll pause the recording and continue with the computational section in, I'll give you all 10 minutes, okay?